blame the Romans.
It's kind of cool.
The Romans did that. What about 10? Do you know? Do you happen to know?
Stadium.
From also the
I'm
Romans?
fairly certain it's also Roman.
All right. And they didn't even do anything. So what do you see as you go to heavier and heavier atoms? And like we talked about, right? You know how to do this. You set the experiment up. All you got to do now is put another layer of some other stuff. You know, and it's like your bang for the buck drops precipitously as you keep measuring these things. So what do you notice?
Yeah, I think the drop is later, but the energy going is lower.
What? Say again?
I may be slightly wrong on what that
Sorry.
signal is, but it looks like the energy is lower, but it drops later.
Okay, this is not energy, and I understand the confusion because we were drawing energies all last time, and we're going to do that again, but we're not drawing energy this time. We're drawing this rho, which got jammed up against the oxygen. That's rho. It's the density.
So,
So, now go.
Well, in this case, the densities are lower, but they last longer before the radius.
The more nucleons I have, that 197 is neutrons plus protons, so that's the number of nucleons that are in there. The more I have, the bigger it gets. And apparently, the lower the density. That's kind of odd. Until you remember, what are you scattering off of these? You're scattering a charged particle off of these. You're sending a charged particle in, and what is it bouncing off of? What do charged particles bounce off?
The nucleus.
Other these are definitely the nucleus, right? But they bounce off other charged particles, and which of the particles in the nucleus are charged?
proton.
The proton. So all I really get to see are the protons, right? The electrons are outside. They're like, it's, you know, out of my way.
We hit those right now.
Yeah, they can just, it's like they're not even there. So the alpha particles bang through there, or the high energy electrons tell the low energy electrons, you know, get thee behind me. They're going in and they bounce off these other charged particles. So all I see here, this is not rho, this is really rho of the protons. And so what I've got to do is I've got to figure out how do I correct from the proton density to the total nucleon density. So, to look at that, I'm going to give you the answer, and I'm going to give you a little bit about how to get there. So, equation 15.8. I think Dunlap has it too, but I'm not sure what. Oh yeah, here it is. Equation 320, Dunlap. They both amount to the same thing, that the density of protons is approximately equal to the number of protons. No, I'm going to write it the way he does, because it's, I actually I'm not that happy with them. Oh no, it's okay. Yeah, the ratio of the densities. So the density of protons to the density of nucleons, which doesn't have any subscript. So you got to be careful and listen carefully to what I say, and hope I say it right. Neutron is one of the two. Nucleon is both of them. Whenever I need to talk about both of them together, I will talk about nucleons. That is equal to, we claim, Z over A. Z is the number of protons, A is the number of nucleons. So these proportions, and so from that, it's not too difficult to show that the density of neutrons over the density of nucleons is N over A. Now that assumes the mass of a neutron is the same as the mass of a proton, and that the radius of a neutron is the same as the radius of a proton. Now those are not true. In fact, we know the mass of the proton and the mass of the neutron. You can measure those in a way that we're going to talk about in a second, and they're not identical, but they're pretty identical. So we're not too far off when we do this. I'm going to give you a couple of things to work on to help set some of this stuff and help you think about it, and do it, don't do it, it's your call. But if I want to talk about the density of protons, that will be 1 over 4/3 pi r protons cubed divided by, Z number of protons you write it this way. Z times 1 per 4/3 pi rp cubed over A times 1 over 4/3 pi r nucleons. So I'm not going to put a subscript for a nucleon. P will be proton, N will be neutron. So what is this telling me? This is telling me the volume per of the protons, the density of protons, however many protons I have times the density of each proton, 1 proton in this volume. This is all the nucleons, A times the density. A lot of stuff cancels there. This is rho protons over rho. A lot of stuff cancels, 4/3 pi, 4/3 pi, but I've still got my R over RP cubed. So this statement, Z over A, depends on this ratio being the same. And later on, we're going to talk about masses, so I'm going to do a little bit about what happens if you have a mass. If I were to calculate the total mass density, these are the number densities. And that's what he talks about in the textbook, and both of the textbooks talk about that. So this number density would be 1 over a distance cubed, or number over a distance cubed. All I got to do is multiply by the mass of a proton, the mass of a nucleon, and I now have the mass per unit volume, kilogram per cubic meter. We will do that here directly. And so it depends on these two things being the same, and we know they're not the same. And so to give you an example, we'll look at this. Can I erase this stuff over here? I haven't done much. So R, this is the average R of a nucleon. This is the radius of a proton. So R will be RP times some small number. And I think in calculus, y'all use epsilons for small numbers, epsilons and deltas. It's like a rule. So if I cube both sides, and I haven't really made my life any easier unless I realize what? What can you tell me about epsilon? This is the average of the neutron and proton radius. Given what I've said, what can you tell me about epsilon?
It's very small.
Yeah, pretty small number, right? It's whatever it is, right? It's 0.00 something or other, but whatever it is, it's a pretty small number. So what happens if I take that small number and square it?
Even smaller.
Even smaller, and about if I cube it. So in fact, I'm not far wrong if I just call that 1 plus 3 epsilon. And so this is approximately Z over A onto 1 plus 3 epsilon. where now I can get a feel for how far off I am. And in fact, if I really want to roll up my sleeves, I can actually correct for that slight difference. I can include that and just do more algebra down the road. But you're in a position now to say, okay, I'll look up, I'll figure out what this epsilon is. I don't know if it's faster to Google it or to figure it out yourself. Anybody know? Yeah, that's always the problem. You never know if it's faster to Google it or figure it out yourself. So you guess. So either Google that or figure out what it is yourself and see what is the error in making the assumption that those numbers are, that density of protons over density of nucleons is Z over A. About how far off is that? You could express that as a percent or a fraction or whatever you want. But that will make you think about this, I think. That's my goal. Might do the same thing for the mass later, but. So conversely, since I have rho P, I can actually now write down rho equals rho P times A over Z. So I can correct all of those. So somebody tell me, what is A over Z for 10? And I'm gonna, while you're doing that, I'm gonna look for where this is. What's that one of those? I'm guessing roughly what that is from figure 3.8. You could also look on figure 15.6 and do it for iodine. And that would just be you getting ready for, you know, a certain date, if you know what I'm saying. Anybody? 2.36. Assuming I'm right, about 0.068, multiply that by 2.36.
.16.
0.16. Which, if you look at figure 3.9, iceberg doesn't do one. So Dunlap, figure 3.9, that's about where the correction happens. You might decide, okay, let me do oxygen 16 and gold 197. See what you get for that. How many of you are going to be freaked out if every single one is 0.16? Well, as freaky as that might have been, now it won't be, because now you expect it. And that's what those figures show. So figure 3.9 in Dunlap shows that all of the atoms approach a fixed nuclear density in the middle. There's a pretty constant nuclear density. They all have about the same density of 0.16 per cubic femtometer. Not my fault. And so that's the correction that you have to do, right? Your experiment is only sensitive to charged particles. You care about all of them, but you can't measure all of them. And so what you do is you say, okay, I happen to know that neutrons and protons have about the same size, and I happen to know they have about the same mass, and so I will make this assumption. And sure enough, they all turn out to be about the same. So in hindsight, you say, well, yeah, I'm probably right. They have a uniform density in the middle, and then it drops to 0. And we're going to talk about how it drops to 0 in a second. Everybody okay so far? That's already, that's news, right? They're all the same density throughout the middle. They have a squishy outer area. They don't go from nothing to something immediately. They go from something to nothing over a distance that we're going to write down in a second. But this is the sort of thing that's going to motivate the models that are developed. We're not going to do it. So we know something about the size, the density of them. Oh, I should talk. Anyway, I'm going to do this a little bit out of order because we're already talking about this. I think I may have said this already. Did I write that already? So it's in both textbooks, and it's the model that really fits the data well. It fits all of those pretty well. And if you think about what happens when I take R near 0, what do I get? Tell me what happens when R equals 0.
Zero over 2.
Not 2. R is going to be 0, but that whole top isn't going to be 0. It will be in a minute, but not now. And 1 plus, what do I get when I put R equals 0?
E to the negative A over B.
Exactly. We're going to find out in a minute that A is much bigger than B, and so that's really pretty close, but not quite, rho 0. So that rho 0 really is pretty close to rho when R equals 0, the density at the center. And that's a small number, not quite 0, and so if you look carefully at some of these graphs, it turns out they don't go exactly to the same 0.16. There's a slight difference in that plateau. And you can probably explain it with that. I haven't tried to do that. But this predicts that if A is different for different atoms, and it is, different nuclei, then you're going to get a slightly different number here, a slightly different R equals 0 density. But they're really close. If you look at that, they're slightly different. So, now put in rho when R equals A. What do you get?
Rho 0 over 2.
Perfect. So if I want to know what A is, what I do is I go to my graph and I read across to where the density drops by a half and read off my R from that. So I'm going to do that for gold. Where's the 9196? Already did that. same thing. I go to the other graph, 3.9, and I look for the half height. Where was it half as big? Where does that happen? I read it off of the graph. I got R about equal to, where are you at? 6.8 femtometers. That's what that is. Then, now what if R equals A minus B? Calculate that. I'll do the top. 1, he did his part. Now what? R is A minus B, go ahead.
E to the negative 1.
E to the minus 1, which is approximately 0.73, row 0. I do that, and I got a R about equal to 6.3 femtometers. Tell me what you read for rho equals R, when R equals A plus B. Just E. Just E to the plus 1, but just E. Equals 0.27, row 0. So what do? I find where that drops to 0.27 of its maximum value. I read off where that is. R is about equal to, what did I get? 7.3 femtometers. So from that, I can now figure out what B equals. Matter of fact, I can figure out what 2B equals. A is 7.3 femtometers. I can read A off of that graph. Right? I find where it's half as big, and I get rho naught over 2, and I get A equals 6.8 femtometers. Then I say, well, go back B. That's when it's 0.73 of its maximum value. When I read that off, I get 6.3. So that means A is now from 6.8 to 6.3. When R is 6.8 femtometers, I'm at A. That's when R equals A. So this is A. This is A minus B, and this is A plus B. So what is twice B? It's the difference between this one and this one. And how are they different? They're different by 1.0 femtometers, or B equals 0.5 femtometers. Now I did that for gold. If you really want to understand what I've done, do it for oxygen and tin out of Dunlap, or do it for carbon 6, or calcium, or vanadium, or cobalt, or indium, and so iodine. What's SB? Romans again? Antimony? Say again? Antimony. Gold again, bismuth. So you got a lot of choices. Pick a couple of those and do it. Make sure that you understand how to do this. That's how people find all these things. So now I know that B is 0.5. What you're going to find out, you're going to get different numbers for A. And if you look at those graphs, you can kind of see that already. A is getting bigger as I increase those atoms, the nuclear masses. But notice those all kind of slope down in the same way. the range over which they drop from maximum to minimum seems kind of consistently about the same, and in fact it is. You get around half a femtometer, no matter what it is. So what we figured out is we now build nuclei by building spherical objects that have about the same density, 0.16 per cubic femtometer. That core area that's really uniform density gets bigger as you increase the number of nucleons until you get to a certain range at which they then drop over about 1 femtometer from the maximum in the center to the minimum outside. They all have that same skin that where the nuclear density drops to 0. It's always about the same thickness, but the core gets bigger and bigger as they get bigger and bigger. And if y'all get together and coordinate and everybody do a couple of different atoms, you would then have 2, 4, 6, 8, 10, 12 different atoms, nuclei. You could then consider, is there a relationship between A and A? Not my fault. Little a is the radius of that core, but essentially it's the half point. Remember, it was where the density dropped to half. So it's to the middle of the squishy peel, I guess, whatever you want to call that. It's to the middle of that. Is there a relationship between them? And what you find out is that yes, it's about 1.0 femtometers times A to the 1/3. Does that seem intuitive, that it should go like A to the 1/3? Well, if I have a certain volume, that would be like 4/3 pi r cubed, right? Could I solve that for r? And in fact, if I have a certain number of them, A of them, if they each have the same volume, then this V would be the number, the volume of a nucleon times A to the 1/3. So in fact, this 1.07 is even telling you something probably about the volume of a single one. Salute. A is 1, 1 to the 1/3 gives you this. So from this modeling, this regression that they did on this data, you get, that should be the radius of a single one with the 4/3 pi. What if it's not 4/3 pi? Maybe they're cubes. If they were cubes, it would still scale like A to the 1/3. These were Lego bricks, right? And you block them together. The volume goes up like the number of Legos that you use. So the size of a Lego is going to be however big your sculpture is to the 1/3 power. So yeah, it is kind of intuitive. If these are hard little things that don't squish together, right? Boom, boom. They're like little BBs, ball bearings. Okay, so now I want to talk about the mass. This is the size of the core, their diameter, their physical extent. Talk a little bit about how you can measure them. So you start off with a magnetic field. And get a charged particle, so it has a charge Q and a mass M, and a velocity V entering that magnetic field. What happens when a charged particle at speed V enters that magnetic field? It's going to turn, and that's important, right? There's a force that is at right angles to the velocity. So it cannot do work. This magnetic force can't do work. You can't speed it up or slow it down. All it can do is make it turn. In fact, because of the way I've set it up there, that's at right angles to each other, and so F will be QVB in which direction? At that particular instant, it would be up. So there's going to be a force perpendicular. It's going to start to turn. It's going to get to here. At that point, is it going faster or slower?
It's the same speed.
Thank you. Yes, exactly right. I can't change the velocity. I can't change work. Sorry, I said that wrong. I can't change the speed. I can't make it go faster or slower, but I can change its direction. That's all I can do. Change the direction. Now, which direction is the velocity? Is the force? B still in. That way. So always in. So if you want to, you could call that minus the radial direction. If radial is out from the center of this circle, then minus R is towards the center of the circle. So that's really a circular path, and that force is, we would call that a centripetal force. It's the force towards the center that's keeping it in that circular path. So QVB is mv squared over r. That came from ma. A is circular motion, so A is v squared over r. If you need me to go over that, I'm happy to do it. So that will make a path, a circular path of radius r. R will be m over q onto, one of those v's goes away, v over b. Now, if I could measure this R, and I can, and if I knew what V was, we'll talk about that in a second, and I know what B is, I can find the mass. Or at least I can find the mass to charge ratio. So I'm talking in a second about how to find V. B, I engineer. I build this device to have a magnetic field. And in fact, I build it to have a uniform magnetic field in this region. That's not trivial. There are ways to do that, but there's a lot of engineering in getting the magnetic field to be uniform in that region, over a region big enough for this stuff to bend and hit my detector so that I can see it and count it. So I measure R. I engineer B. I need to know what V is. I want to get M. I gotta worry a little bit about that Q. The V, how do I get the V? Well, one thing I do, I could just have, if these are positive charges, I'm gonna charge this plate, these are two parallel plates, capacitor. This capacitor has an electric field in there. I boil the electrons, the ions, they need to be ions. I'm going to heat them up so that they will strip off an electron, so I'll have a singly ionized whatever it is. Now I want this plus charge to go that way. How do I charge up my plates? Which direction is the electric field if I want it to go that way?
Is it that way?
You're overthinking it. It's positive charge, I want the force this way.
So the electric field has to go to the right.
The electric field's gotta go in that same direction. So I create an electric field between these. Now, to get an electric field that points that way, where's my positive and where's my negative charge gonna be?
Positive is gonna be on the left, negative is gonna be on the right.
Starts on positive charge, ends on negative charges, so good. Where's my voltage gonna be high? Where's my voltage gonna be low?
Like voltage or negative, low or positive.
So this has gotta be high voltage. Electric field points in the direction of decreasing voltage. And so the kinetic energy of this particle as it approaches this plate on the other side will be its charge times that voltage. So my engineering is I raise this to a high voltage, I somehow get these these nuclei in there, singly ionized, so they're a plus charge. Now I know what that speed is. Because I know what this voltage is, I want it to be singly ionized. Oh, I don't really know what the speed is, do I? The whole point is I don't know the mass, do I? Right? I'm trying to find the mass. So, I get them going, and they have some speed, and then now I have my ingoing magnetic field. I now create another electric field. I have what I believe is a positive charge going in that direction with some speed v. Which direction is the magnetic field? Force. Field's in. Magnetic force is V cross B up. Now, it's a magnetic force. I now charge these plates that way, so I create a downward electric field. At this end, I have a little opening, and I tune this electric field until this electric force is balanced by that magnetic force. Everybody okay? I can adjust this electric field by adjusting that voltage. This is my acceleration voltage. This is going to be called my selection voltage. So I have another voltage that I set here. I create a downward electric field. I tune it till I balance these two. What does this charge do if the electric and magnetic forces are exactly balanced?
Just keep going straight.
No acceleration, no net force, no acceleration. It'll go in the same direction at the same speed. So whatever speed it is, it'll keep going in that same direction. If it comes out this hole, then I know that the magnetic force is exactly the same as the electric force. Do I know V? Well, if I know this voltage, I can get that electric field. I know what magnetic field I created. Q cancels. So I don't know anything about the charge from this, but now I know exactly what velocity I've selected. So it's a good name for this thing that selects velocities.
Selector.
A velocity selector, yeah. Again, people gave us quarks. So now I know the speed. I tune the speed by adjusting this electric field given that magnetic field. I now know how fast that charge is going. Now I know V. I know that it's a positive charge because I know only positive charges fly off of this plate and smash into that plate. That's a problem. What do I do about that? I've got these two plates charged up. And that gives me the electric field that causes these things to accelerate, but now they bang into that. How do I get out of that?
Could you put a hole in the plate on the right?
I pretty much have to, right? I pretty much have to put a hole. At least one hole. In fact, you can put a bunch of holes on there. You can make actually a grid, a screen that's got lots of holes in it. That will change this electric field, but not as much as you expect. The electric field out here won't be quite zero, but it'll be really small. And so it works almost exactly. Now, how much exactly? Well, now you gotta roll up your sleeves and do really hard calculations to figure out what is the field really. What is the real kinetic energy when it comes out? Same thing here, right? I mean, we've thought about it in a very simple way, but it actually, the engineering is much, much tougher than the physics when it comes right down to it. But now I know V, I know M over Q, and it turns out I can't get past that. I have to worry about the fact that I'm really sensitive to M over Q. I'm really finding the mass per unit charge. So if I have carbon with one fewer electron, so it's got a net positive charge. Is there a 24? Yeah. Magnesium with 2 electrons would also have a ratio of 12. M over Q would be 12. So I would be sensitive to carbon 6 and magnesium 12. They both have the same ratio of mass to charge. It's just if I'm careful, if I keep the, if I'm not too aggressive in ionizing those atoms, I'm much more likely to have a singly ionized carbon atom than a doubly ionized magnesium. Now, if I know for sure that I have carbon, right, if it's highly purified carbon, then I'm golden, right, as long as I don't have to worry about it. But if you're doing things like, here's a rock, tell me what's in it. And then you've got to worry a little bit about getting doubly and triply ionized species. But that's essentially how you get tables like, yeah, and he talks about it in 15.4. Or, I'm not sure where. That's how you get all the masses. So now I know all the masses, I know all the sizes, I can start thinking about how to model these things. Oops, sorry about that. Suspected spam call. Everybody okay? Kind of got what's up here? Oxygen, 8, 16. 8 protons, 16 nucleons. The mass of that should be 8 times 1.672 times 10 to the minus 27 kilograms plus 8 times 1.675 times 10 to the minus 27 kilograms. 8 protons, 8 neutrons, ever so slightly different, but not much. Really pretty identical. That's 26.776 times 10 to the minus 27 kilograms, or 16.1204 AMU, or atomic mass units. That is all over iceberg. I'm not sure, I think Dunlop doesn't use it because it's kind of fallen out of favor, but. However, if I put the oxygen in my mass spectrometer, that's what that's called, that little magnetic field velocity selector thing that finds masses, called a mass spectrometer. It turns out to be 26.568 times 10 to the minus 27 kilograms, or 15.9949 AMU. So what did we discover? One thing, Mr. Pi over 3 is 1. Have I done this to you guys yet? I think I have, right? In fact, more than once. Mr. Pi over 3 is about 1. Suddenly, I'm like writing down more decimal places than you could imagine. You might see why I did that. I would have lost this difference if I'd rounded everything up. You just got to bite the bullet, because these differences are small and highly significant. So, anybody, any ideas? What would the theoretician say when an experimentalist comes in and says, I measured 15.9949? And the theoretician says, no, it should be 16.1204.
You assume the experiment was done wrong?
Yeah, go back and do it again until you get the answer I want you to get. And so they got to go back and prove that they did it right. In fact, they want to do it right. So eventually, they've got to resolve that difference. And so that difference in energy, that difference in mass is interpreted as a binding energy. And you can calculate that energy in joules from that mass in kilograms just using Einstein's equation. So for this set of measurements, that's 0.208, 0.208 times 10 to the minus 27 kilograms times 3 times 10 to the 8th meters per second squared. I'll get 1.872 times 10 to the minus 11. What's a kilogram meter per second? That thing squared. It is a joule. Or 1.1169 times 10 to the 8th electron volts, or 117 mega electron volts. First time you see that, and then quickly on a per nucleon basis, if I do the binding energy over A, that's 117 mega electron volts per 16 nucleons, or 7.3 MeV per nucleon. So, just to try to understand what this, find the binding energy for iron 56. But when you first see that, especially if you're a chemist, you're freaking out. Because when you do chemistry, what sort of binding energies do you have? Anybody happen to know?
I was gonna say chemicals.
It's chemists? Yeah, it's their problem. Well, it turns out it's on the order of electron volts. Binding energies in chemistry are around a few electron volts. How much is this? This is 1,000,000 times, 100,000,000 times more bound up in those. And so you can imagine, if I could break those apart or put them together, which they knew was going on anyway. They knew that things broke apart radioactively and could be put back together radioactively. Now suddenly you know, wow, if I could put that all together in one place, that would be pretty amazing. That would be a way to power society forever. 100,000,000 times the energy that you get from fire, from burning coal, from burning, and of course, what was done first with it before they started powering things was the nuclear weapons that they built at the end of World War II. But it all starts right here. It all starts with the idea that that's 100,000,000 times more than you get from a chemical process. And so this is huge, this is big. And that's why they were very, very secretive about the whole thing, all through the 10s and 20s and 30s when they were figuring this out. What you're going to find out when you do that, you're going to get a different number. And if you look at figure 4.1 in Dunlap, or figure 1510 in Iceberg, you can see that it differs quite a bit. That as you start with small atoms, they start here, it goes up and then down. Part of our goal is going to be to understand that figure. So this is binding energy as a function of, it's down there, A. And it's binding energy per nucleon. So you're looking at what is the binding energy per nucleon. So what you see from this is that if I'm here and I split this in half, I go there. There's less energy around. I've got to provide that energy. But if I go this way, I get that energy. From here out, when I break things in half, I get energy. When I fuse things, I get energy. If you do helium, helium is 4.0026 minus 4 times 1.0078 units. It's minus 0.0286 units. And multiply that by 931.5 mega electron volts. What could that possibly be? Well, it's obviously the conversion factor between mega electron volts and atomic mass units. And you just Google that. You can calculate it from the mass of a proton, but it's easier to just Google it. So that's minus 26.64 mega electron volts. So I'm fusing 4 hydrogens that I start with to helium. I get energy. If I break uranium-235 into, for example, zirconium-100 and tellurium-135, at the end, I have 99.91776. I Google these, plus 134.91645, minus 235.0439. That's negative 0.2097 times 931. 31.5, or 195.3 mega electron volts. You can think of this as empirical. I measure these things, I can do these calculations because I find the masses and I can get the delta M. So far it's just numerology. So the question then becomes why? Why does it matter? First off, why does you get anything? If the binding energy per nucleon were the same, no matter what the atom is, then it wouldn't matter. You wouldn't get energy by breaking them apart or fusing. Why do I get energy when I fuse small things, but I lose energy when I fuse big things? If I fuse these, I lose energy. I gain energy when I break them apart. Except for that one. I don't get anything from that one. Anybody happen to know what that is?
So an iron.
It is iron.
Oh,
So you could argue, go ahead.
I was gonna say, that's why everything's slowly turning into iron.
That is the argument that says over time, that's the one stable thing that never goes anywhere. And so some people speculate that, yeah, given enough time, the universe would completely turn to iron. It'd be all iron 56.
That's why stars start to die pretty quickly when iron starts to form,
Once
right?
they start to form iron, they got nothing. Yeah, they can fuse stuff all the way to here. But now they lose energy when they fuse. So yeah, once they start making iron, the game's up. So then the question becomes, the important question becomes, I can understand how atoms make, how suns make everything up to iron. So I look around me and I say, okay, yep. Stars, the original universe made hydrogen, helium, and a little bit of lithium. Where does everything else come from? Okay. But where does all this stuff come from? Certainly doesn't come from the inside of a star, at least not at equilibrium like these processes. Turns out all of those things come from supernovae. That's when things are not happening equilibrium-wise. They're not slowly just day after day doing the job, putting stuff together. That's when they blow up and things get fused beyond where it makes sense. So when it costs energy to make them, they do it anyway because they're blown up. So then, to understand this shape, you take a clue from a few of the things we've seen. One of the things we've seen is that we put in more stuff, we just get bigger spheres. Well, what else happens when you get things and you make them bigger? You add stuff and it gets bigger and bigger and bigger. Pretty much everything. Solids do that, but solids have weird shapes. What makes a spherical shape and has a constant density as you keep adding more stuff? Liquids. Liquids do that. So we start off with a liquid drop model. We start off talking about a nucleus as a drop of liquid. And we're going to figure out that mass, that binding energy curve, by figuring out what a liquid drop of these impenetrable spheres, how it would behave. So, we got one nucleon. We're going to do this in a row for a while just to get the idea, and then we're going to go from there. No bonds, because that's just one nucleus. Now, add another nucleus. How many bonds? If they're stuck together, in the first one was the proton, right? That was, or a neutron by its lonesome. No bonding, right? Just by itself. We're not up to helium. This could be a deuteron, but we're going to find out it can't be two neutrons and it can't be two protons, but it can happen if it's a neutron and a proton. We actually can get two of them to go together, but it only happens when the two are unlike, and that'll be a quandary that we're going to have to figure out. But how many bonds do we have? Just the one, right? If we do it in one dimension, and I'll put this one here, I have 3 nucleons, that gives me 2 bonds. So 2 bonds. And if I add another one, in other words, so far what I have is that the number of bonds goes like the number of nucleons, A. I wrote N in my notes, but I already used N for neutrons. This is nucleons, A. So that's if I only let them interact with a neighbor. But now what happens if I let them interact with, if every one of them gets to interact? Imagine that those were charges. If they're protons, they are charges. That'll be relevant when we start trying to add on to this. If only neighbors can interact, I got 1, 2, 3, 4 bonds. Right? Bonds goes like A. But what if I let everybody interact with everybody? If they're protons, that means these two repel each other, but so do these, and so do those. Tell me how many bonds I have. Okay, it's going to be 1, 2, 3, 4, 5. Choose 2. I got 5 particles, and they're going to interact in pairs. So it's going to be 5. Choose 2. Because if I do this one interacting with that one, I can't overcount it. So it's going to be, that's called a combination.
Is that a multiplicity?
It's related to multiplicity, and it's the same idea as multiplicity in thermodynamics. Is that what you're thinking about?
Yeah.
Yeah. Yep, you do exactly the same kind of calculation. But there you're doing configuration. How many ways can I arrange this system? So, number of bonds will be like B, the binding energy that we've been talking about. And what do we find out? Oh, sorry. So that's going to be A factorial over 2 factorial A minus 2 factorial. So that's going to be roughly A times A minus 1. So I'm blowing off that half. There's a half in there that I've just completely ignored. A factorial over A minus 2 factorial is A times A minus 1. This is a small enough number, you should be able to write out every single one of them. Give these names, right? 1, 2, 3, 4, 5. One of your interactions is going to be 1 to 2. Another one of your interactions is going to be 1 to 3, and so on. You should count up 20. There should be 20 of them. 10 over 2. 20 over 2 would be 10. If you want to understand what I'm doing here, go through the motions of doing that. That's my recommendation. But when we look at that graph, there's some weirdness over here, but for most of this, B, you can get close if you just said B is about 7 or 8 MeV. From this picture, B over A is about equal to 7 mega electron volts, pretty constant. Yeah, it goes up, it's got some structure, it's got these way down here. All right, gotta worry about that. But most of that, B over A is a constant. This is the only thing that makes sense then. These long range interactions says that B over A should go up like A. B over number of bonds, the binding energy, should go like A squared, A times A. So that means B over A should go like A, should get bigger. The binding energy per nucleon should get bigger for bigger nuclei, if they're allowed to interact, all pairs. What this tells us is no, B over A is roughly constant. That means B goes like A, not A squared. That means this interaction, whatever it is that's holding these nucleons together, doesn't reach across to the other side. If you're on the left side of your gold nucleus, you got nothing to do with the nucleons on the right side of the gold nucleus. Who do you interact with? Just your nearest neighbors, just the people nearby. And we got that just from looking at this data so far. We haven't had to work that hard to draw a pretty important conclusion that the nuclear force is short range. It's not long range like the Coulomb force. Coulomb force reaches through, right? So think about krypton. Krypton's 36. So you got a couple of electrons in the middle, a few more on the outside, a few more on the outside, a few more on the outside. The protons in the middle are reaching all the way through all those electrons and interacting with the electrons on the outside. Because if it didn't, they wouldn't stay. Those outer electrons are not being pulled by the other electrons, they're being repelled by the other electrons. This nucleus has to somehow reach through all those other electrons. That's a long range force. Think about gravity, right? What's pulling you to the surface of the earth?
Every atom in it.
Every atom in it, and that's the point. Every atom in it. Mostly the iron core. So it seems weird that the sun's gravity can reach through empty space to the earth, but how much weirder is it that the iron core can reach through solid rock and pull on you? So that's what you mean by long range forces. They reach through stuff. These are short range forces, and we figured that out just by thinking about how they could interact and looking at what the data tells me. The data tells me I'm not there, right? I've got some structure I gotta worry about, but I'm pretty close. So I already have a term in my semi-empirical mass formula I want to understand this formula. I start off with saying the binding energy then goes like A1A. This is the iceberg notation. He uses A sub V. Dunlap calls this A sub V A. Does he have the minus sign? No. He writes it as a positive binding energy holds you together. That's Dunlap. This is iceberg. And let me make sure he writes it as a negative number binds you, so not my fault. Those numbers should be close to the same though, right? whether you call it binding energy a negative number that binds you together, or this is how strongly you're built, you're bound, that number should be close to the same. Our leading term, and we expect that number to be around 7 or 8. Might be different once we add the other terms, but we expect it to be 7 or 8. MeV per nucleon times the number of nucleons, that gives me that line. I'll give you a second, take a deep breath, because we got to start talking about okay? Do the next step. Because now we're in 3 dimensions. So these, every atom only has 1 neighbor. 2 neighbors, right? So number 2 interacts with 1 and 3, 3 interacts with 1 and 4. If you put them in a plane, right, they might have 6 neighbors if it's hexagonal pattern, or they might have 4 if it's laid out on a grid. If it's 3-dimensional, if it's a tetrahedral pattern, right? They got 4 of those, so they'd have 3. I'm not sure how many. They'd have a number of neighbors. That will differ a little bit according to exactly how those are packed in there. But the packing tells you how many neighbors they have, and it'll be a fixed number. And what happens though when you get near the end? Think about it in 1 dimension. This happens in 2 and 3 dimensions, but think about it in 1 dimension. What happens? Number 2, how many neighbors? 2. Number 3. 4. Anything different? 1. 5. Yeah, the 1 at the end, right? They only have 1 neighbor. In a square, the ones in the interior will have like 4 or 6 neighbors, but what happens when you get near the edge? They don't have as many. Yeah, they're bereft of neighbors. Same in a three-dimensional. So there'll be something that depends on the surface. Something related to the surface. If you're near the surface, you won't have as many neighbors. That reduces the binding energy. Right? I've got all these ones in the volume that are bonding with all their neighbors, and then you get near the surface, and because you have an edge, you now have not quite as much binding as if this were a neutron star that went on forever, right? You had nothing but nucleons forever. In this case, you have a surface. And so then the next one is called the surface term. And it depends on the surface area. And Dunlap writes it as a reduction in the surface times a to the 2/3. He does the same thing, except he calls it A2. There's another sign goes the other way. He has a plus A2 to the 2/3. So this is just a proportionality factor. We're just going to change that till we fit the data. So there's no physics in that yet. There will be some eventually, but nothing yet. But why do we say it goes like A to the 2/3? Anybody remember what that was?
I was gonna say density from my brain.
We were using it to get the density.
Yeah.
It was a part of that equation. We got it from looking at masses and the sizes and looking how they scale. What was that? Anybody remember? Now you have to participate. Can't be the only one performing. Flipping back, it's gotta be in there.
What's the radius to the middle of the squishy?
So starting
Here we
from
go.
the center of the nucleus out to the middle of the layer, that was what that was. That's the radius. If these are spherical molecules, that's the radius. How do you write the area of a circle, of a sphere? 4 pi r squared. He said so quietly that only I could hear it. And if I put in this for r, what do I get?
You get 830.
I get some stuff in front times a to the 2/3 power. Now I could try to stuff that in there and actually work, but the problem is I don't really know what the packing is. I don't know exactly how those nucleons coat the surface. So I just leave that as a parameter that I'm going to use to fit data. But the bigger I make that sphere, the bigger the surface is. When A gets big, the sphere gets big. And how big does it get? A to the 2/3. And I'm 4 minutes over and I apologize. You guys got to tell me. So we're doing the semi-empirical mass formula. Why is it a mass formula? Because the binding energy is directly related to the mass difference. It's empirical because we're using measurements we made to figure it out. We're not calculating it from basic physics. But it's semi-empirical because we're going to wind up using some physics to guide us in writing out the whole equation. But at the end, we're just going to fit it and get the parameters out and call it good. Then we'll try to understand some of why it has the form that it has. But if you want to know where we're headed, it's the liquid drop model in there. It's the liquid, they both call it the liquid drop model. But I promise you, I've heard it referred to as the semi-empirical mass formula. So that's another thing to Google.